Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I will go over double integration in polar coordinates. We did the single integration before. Today, we are going to look at the double integration. And to make things easy, like we always try to do, is we are going to look at the easiest shape, which is a circle in polar coordinates, really, right? No, the equation of a circle is r equals whatever, the radius, r equals 3, for example. That's it. That would be a circle centered at the origin, but of course, we learned many other shapes and how to plot them uh, in polar coordinates. Here, I'm going to look at a small sector with an inscribed angle here of d theta. And remember last time we were using only one variable, which was theta. Here we are going to look at a very small piece of width dr, and the angle here is d theta, and these are as r and theta approaches zero, right? The limit. And if we say that distance from the inner arc to the center is lowercase r, then if these are too small, you get a rectangle. Remember in the case of, so D area, in the case of Cartesian, we said it was dx dy because it was a rectangle of width dx and height dy. In the case of a polar, we learn that the length of this arc is r d theta, right? R d theta. I'm going to write them away from each other because the width is dr. So usually we write the r next to its derivative. So r dr d theta is the equivalent of dx dy. That's it. After that, you integrate the same way. The only difference, of course, is that you need to learn how to find the limits of integration. So let's take two examples today. I'm going to take the first example where an integral is given to you in Cartesian, but it's not solvable. You can't really do anything about it. And then we'll take another problem where we ask you to find a volume of some kind of shape, some shape. So in the first example, they told you we have an integral here. It's a double integral in Cartesian, and it says cosine of x squared plus y squared dy dx. How do I integrate cosine x squared plus y squared first with respect to y and then with respect to x? I'm not sure. And they tell you the limits of integration for the y goes from 0 to the square root of 1 minus x squared. Do you know what that is? You should, okay? But we'll talk about it. And dx is from -1 to +1. Okay, so if I try to plot the area, this shape, I don't care about the function, okay? The function will be multiplied. I just need to find what is the domain or the area that we are integrating over, right? Now, if I say this is the y, right? The y goes from 0 to the square root of 1 minus x squared. So if I square both sides, I know that y squared would be 1 minus x squared. If I add x squared to both sides, I get x squared plus y squared equals 1. That's a circle of radius 1 centered at the origin. But is it the full circle? No, it's just the top half, right? Because it's a positive root. The negative root would have given me oh, the lower half. Semicircle, we can draw it, enlarge it so that you can see what we have here. Here is the origin. It goes from, so the y goes from 0, which is the x-axis, to this circle. The x goes from -1 to +1. So really, if I didn't have the cosine of x squared plus y squared, and I integrate just dy dx, I will get the area of this circle, which is pi over 2. It's pi r squared over 2, but r is 1, so you get pi over 2. You don't need integration, you don't need polar, nothing. What makes it hard is cosine x squared plus y squared. Because when you say integrate dy dx, and I don't know if I made that clear last time or not when we were doing the Cartesian integration, if you don't have that, it's as if we are telling you we have a half a circle, and the height of that circle is a unit. So when I integrate, I can get the volume. If that half a circle has a height of 1, its volume would still be pi over 2. It's pi r squared times the height, which is 1. But when you multiply it by something, you say, oh, that's not a uniform height. This at this point, x is 0 and y is 0, so you get a height of 1. When you go, say here, x is -1, so x squared is 1, but y is 0, so you get cosine 1 and sine 1. And if you go here, uh, if you go somewhere in the middle or somewhere here, at every point you have a different x and a different y. If you square and add them up and take the cosine, you will get a different height. So that shape, I cannot find its volume, which would be evaluated using this function just by using some kind of an equation. I don't know. I know only if the height is 1. In this case, I can find the volume, which would be the same as the area, since I'm going to multiply the area by 1. So that would have given me the area of half a circle of, or the volume of a circle that has a height, a semicircle that has a height of a unit, 1. Okay, so let's put this apart and we say, well, I don't know how to integrate that in Cartesian. But I know that x squared plus y squared equals r squared. And I know that dx dy is r dr d theta. So just substitute. I will get a double integral. I don't know the limits of integration yet. We'll see how we get those. But inside I have cosine r squared. And then outside I have another r dr d theta. I'm going to integrate with respect to r first. Usually that's what we do. But what are the limits of r? Very simple. Your r starts from the pole and goes out. So you start at 0 and end up at 1 in all directions. So there is no function here. It's not 1 minus, it's simply 1. And the and the theta goes from 0 all the way to pi. So from 0 to pi, see how easy it is? Now, for those of you who notice that the derivative of r squared is 2r, meaning if I multiply by 2 and 1/2 here, I will get very easy integrand. Or if that's new to you or you are not confident so far yet, then use substitution. Let's say let u, what makes the problem is r squared, so I would say let u equals r squared, in which case du would be 2r dr. Now, I have r dr, not 2r dr, meaning r dr is du over 2, 1/2 du. 1/2 is a constant. So I'm looking at the inner integral first, inner integral. I'm going to take 1/2 out, take the integral. Cosine r squared is cosine u, and r dr is du. At this point, we have two types of students and two types of professors who like who like what you could do. You have two methods to proceed. I can proceed all the way with you until I get a value, or I can proceed first with you and then go back to R. What I mean is, the first method, stay with you, not with yourself. With the Okay, I know, bad joke. So if you stay with you, you have to find the limits of integration of cosine u du. How do I find the limits of integration with respect to u? I say, well, I made a relationship between u and r. If r is 0, then r squared would be 0, meaning u would also be 0. So the lower limit doesn't change. But if it were, say, -1, it would have become 1. If it were 2, it would have become 4. Okay? You can see r squaring. Same thing. When r is 1, 1 squared is 1. So u stays. So it really didn't matter in this integration, and you can proceed like that. The second method is that you evaluate the integral as if it were an indeterminate or indefinite integral, okay? So you would say 1/2 times the integral of cosine u du, you get 1/2 sine u. And you leave it like that, you don't add a constant. And then you say, oh, but u is r squared. So that becomes 1/2 sine r squared evaluated, look at the r from 0 to 1. So you'll get 1/2 sine 1, since sine 0 is 0, you don't need to say 1/2 times sine 1 minus sine 0, so it's 1/2 sine 1. In the second method, I already changed the limits of integration, so I don't want to go, there is no need to go back to u, right? This integral would be 1/2 sine u evaluated from 0 to 1. Of course, you will get the same result, which is 1/2 sine u. I'm sorry, sine 1. So in both cases, you get the same answer, but one has to go from u back to r and change. So that's a cumbersome step. And the first method also have a cumbersome step, is that you have to remember to change the limits of integration. In this example, it didn't make a difference, but in other problems, it may change. Okay, so as I said, if that was from 0 to 2, here I would have from 0 to 4, since 2 squared is 4. Many students still forget to change the limits of integration, so it would be safer to go back to the original variable and evaluate the integral there. Okay, so now that is a constant value. So now when I go to the outer integration, I see that I'm going to integrate from 0 to pi. 1/2 sine 1 is a constant, 1/2 sine 1. And then I'm going to just integrate d theta. So I will get 1/2 sine 1 times pi minus 0, which is pi. So it becomes pi over 2 sine 1. Notice that pi over 2 was the integral of this area, pi r squared over 2. But when I said, well, the height here is not a unit, right? It's a unit at the center, but that's only where it is 1. It's get lower because the cosine goes from 0 to 1, right? So that's not like a unit thickness. No, it's 1 here, but it gets smaller and smaller as you go away from the center, because x squared plus y squared get larger, and then they will be smaller height, so to speak. So that's the sine 1 is very small value, so that integral becomes very small. Okay, so that's the first example. The second example may include, we are going to include, we are not going to give you an equation or a Cartesian integral. Here we have a sphere of radius, let's make some numbers, with radius 4. We drill, let's say centered at the origin to make it easy. We drill uh, a cylinder through it, but the cylinder also centered at the origin. Of radius, whatever. What do you want to do? 3, 2, whatever. Let's make it 3. 3, it doesn't matter. Find the remaining volume of the sphere. So I have a sphere, and then in the middle, I drilled a cylinder, right? So that would be subtracted from the volume, and I want to see uh, how that is, or what's the remaining volume. We know that the equation of a sphere is x squared plus y squared plus z squared equals r squared. I know that x squared plus y squared is r squared. So this is r squared plus z squared equals 16. But I cannot use the z in the double integral. How? I mean, I only have r and theta. So I have to rewrite z in terms of r and theta. So from here, you can say if I subtract r squared from both sides, I get z squared equals r squared minus 16. Then I take the square root of both sides, and be careful when you take the square root of the right-hand side, you say plus or minus, because you have a top half of the sphere and a bottom half of the sphere. Like the circle in the previous example, we only had the positive root, and we knew that we are dealing with the top half of the circle. If it were a negative, I would have done it to the bottom one. So it's not any different. So here I will get z is plus or minus the square root of r squared minus 16. Okay. Now, if I look from the top to see what's going on, I will have a radius or a hemisphere. Oops, should have went a little, should have gone down a little bit. Okay. They are eccentric, right? And oops, almost. Oh my, oh my. Okay, so here is the cylinder that we drilled. We know that this radius is 3. And that radius is 4. And we want the volume that would result after the drilling. So now I know that my function can be represented as the square root of 16 minus r squared minus negative the root of 16 minus r squared, right? This is the equation that I will integrate times r dr d theta. That's the d volume, not the area now, because I multiplied by that. And I have a double integral. I will say the r goes from 3 to 4. There is nothing inside of 3, right? So 3 to 4. And theta goes from 0 to 2 pi, so that's easy. It's the whole circle. And that will give me the volume. Notice that when you negative times negative is positive, so I will end up with 2, the integral from 0 to 2 pi, integral from 3 to 4 of the square root of 16 minus r squared times r dr d theta. When I look at the inner uh, integral, so the inner integral, and again, I realize that the derivative of what's inside is negative 2r, and I have r 2r outside, so it's negative, just negative du. So again, let's play it safe and work with the substitution, even though you don't need it. U equals the square root, or I'm sorry, U equals just 16 minus r squared. So du equals negative 2r dr. So if I want to take this integration, I'm going to say, I already have 2. So 2r dr, 2r dr is basically negative du. So I'm going to say negative and du. And I have an integration here. The square root of 16 minus r squared is the square root of u. So it's really the integral of negative u to the 1/2 du, which is negative u to the 3/2 divided by 3/2 or multiplied by 2/3. So I get negative 2/3 u to the 3/2. Again, I can find the limits of integration with respect to u, or I can go back and substitute here with 3 and 4. Again, it's the same thing. But if you stay with u, you have to change the limits of integration. Should I show it both ways? Okay, let's say if I stay with u, I have to change the limits of integration. I say when r is 3, r squared would be 9, and 16 minus 9 is 7. So this goes from 7. And if r is 4, you get 16 minus 16, which is 0. Notice that when you evaluate with 0, you get 0, and then minus times the negative will cancel each other, and you will get 2/3 7 to the 3/2. 7 to the 3/2, meaning 7 times root 7. 7 times 2 is 14 root 7 over 3. If you go back, it's identical. Why? Because the answer, or this integral, the inner integration would be the following. Notice that you already have the 2. The 2 was taken into account. So what we end up having would be 16 minus r squared to the 3/2 times negative 2/3. That's what I got. So I simply substitute the u into 16, and then 3 and 4. Notice that when you get 4, 4 squared is 16, so you get 0. So negative 2/3 times 0 minus, and then when you get the 3, you get this is 7, which is 7 root 7. Negative times negative is positive, and you get 14 root 7 over 3. It's the same thing. It's really up to you to decide what you want to do. If you remember to change the limits of integration, usually it's easier. Why to go back and forth? You can do it right there. Later, when you get more sophisticated in doing integration and you see the negative 2r as the derivative here, I could have written this. Should I say it here, or instead of calling that dr, I can call it negative with the 2, negative d 16 minus r squared. So it's as if you are integrating the square root of 16 minus r squared with respect to 16 minus r squared. Later you will find it for yourself, I'm sure. I'm sure you will see it. Now, since we already are done with the inner integral, now I will have an integration going from 0 to 2 pi of a constant, which is 14 root 7 over 3 d theta. So I will get 14 root 7 over 3 theta evaluated from 0 to 2 pi equals 14 root 7 over 3 times 2 pi minus 0, which is 28 root 7 pi over 3. And this is the volume remaining. Remember, the original volume was 4 cubed over 3, 64 over 3 times r cubed. So r cubed, I'm sorry, 64 is r cubed, 64 pi over 3. Okay. And the square root of 7, I don't have the calculator with me here. I think this one works. So let's see. If we look at the volume of the volume of the sphere without drilling anything, it would be 4 cubed over 3. Oops, no, I'm sorry. I always do that. 2 4 cubed pi over 3, right? 4 r cubed. I'm sorry, r cubed pi. 4 thirds. So times 4 again. 4 third pi r cubed. 4 times 4 cube, and then times pi over 3. You get 268. Now what we got is 28 when we cut like 3 out of 4. So we cut a big deal, right? 28 square root of 7 pi over 3. So we are only left with 77 cubic units. Okay. Okay, I hope this was clear. Maybe we can have another session on that. If you have any comments or any problems in your mind that you want us to work out, please leave me a message in the comment or a comment in the comment section, and I will get back to you as soon as I can. Thank you very much for watching. Have a great day.